Mr. Pratt's Physics. Let's get to it. All right, so today we're going to get started with another look at energy. We did some things with qualitative energy earlier on. We found that energy was conserved if we had a closed system and that we had different storage modes of energy. The storage modes of energy that we were particularly interested in that we had looked at were elastic energy, where we found that objects like springs or rubber bands that could be stretched or compressed, this one doesn't compress but it does stretch, would store energy in there, and the more it was stretched or compressed, the more energy it stored. We found that there was kinetic energy, the energy of motion, that the faster something was going, the more kinetic energy it was storing. We saw that there was gravitational energy based on the gravitational field of the Earth, that the higher something is, the more the gravitational energy was being stored in that object based on the position of those two objects. And we looked at some internal energy where we saw in particular of interest to us was friction, whereas friction was present in a system. The energy that was started out as kinetic energy would be turned into a storage mode, start being stored as, for instance, some internal energy, heat in particular, and so on. That energy was dissipated or lost to the system or to the object. A useful energy was lost so that it was now stuck in that internal energy mode. Well, we're now going to take a quantitative look at that. And we're going to start our quantitative look by taking a look at the elastic energy. And we're going to find that the elastic energy, as we saw before, the amount of elastic energy that's stored in a spring is related to how much the string is stretched, how much the spring is stretched. On the other hand, also, we know that in order to stretch the spring, one has to apply a force to it. And therefore, there's a relationship between how much the spring is stretched and how much force is actually applied to that spring. So we're going to start by looking at that relationship. And once we have a good idea of that, we'll use the information that we found there to try to analyze some situations where we can figure out how much kinetic energy is stored in an object, how that's related to how fast something is going. And we'll be able to relate that also to how much gravitational energy is stored, starting from knowing something about this elastic energy so that later when we take a look at what's going on, we can see as energy is moved from one storage mode to another that we have those various storage modes of energy being exercised. So we're going to start by taking a look at this spring. So for instance, it starts off right here at equilibrium, as we would call it. It's not stretched or compressed, it's just in its natural state there, ready to store energy if we apply some force to it. And I'm using this meter stick here to indicate, to take a look at, well, just how long is that spring? So in a sense, we're going to call our zero position when there's no energy stored is the length of the spring right now. And I've got this meter stick, we'll be able to take a look. It's basically, we're at about 28.3 centimeters down, or 0.283 meters is our actual starting position there. So I'm just going to take this here and we'll say when there is no mass present on that spring, or so that the force is actually therefore 0 newtons, the length of this spring is actually 0.283 meters. Now, essentially from here on out, what we're going to do is we're going to call 28.3 centimeters, we're going to call that our 0 point. So from here on out, we're just going to actually measure from the 28.3. As we put more mass on here, we will figure out how long it is from that equilibrium position. So to get started, let's find out what a very small amount of mass does to this. Well, I have here 10 grams, And if I put 10 grams on here, now I have to be very careful how I put that on there because I don't want it to just fall off. There, I've got 10 grams sitting on there. Now we recall that if there's 10 grams sitting on there, the force of gravity that's being applied to that spring by that weight, the force of gravity on the weight is going to be 10 grams, or actually 0.01 kilograms, times 9.8 newtons per kilogram. That will tell us the gravitational force. So actually, on the spring itself, therefore, that mass is pulling down on that spring with that number of newtons. 0.01 kilograms times 9.8 newtons per kilogram would give us 0.98 newtons of force. And when there are 0.98 newtons of force applied to that spring, we see that the actual spring is now 29.1 centimeters down. Well, since 28.3 was our actual equilibrium position, that means we've actually increased by about 0.8 centimeters. So we've increased by 0.8 centimeters. 0.8 centimeters, that would be 0.008, because that's 8 millimeters, 0.008 meters. So we'll take a look here. We've got 0.008 meters. When we had 10 grams, that's 0.01 kilograms for a force of 0.98 newtons. We had a length of 0.008 meters from its equilibrium position. Okay, we're going to continue, we're going to add some more mass on there so we can make a data table of the length of that spring based on the length of that spring, how much force is being applied. Let's go ahead and do that. Let's see what happens when we put 20 grams on there. So if I carefully put 20 grams on here, and let's see if I can get it without having it fall down. Indeed, there we go. And now we see it's bouncing a little bit, but I'll get as good a measurement as I can here. 30.9 centimeters from 28.3 centimeters that it originally was, or 0.026 meters when there were 20 grams applied there. Well, how much force would that be? That would be this 2 times this 1.98, which is 1.96 newtons. It's stretched down to 0.026 meters. And I'm going to now just go ahead and take a whole bunch more data, and then we'll see how that comes out. Here's 50 grams. Okay, I'm going to continue gathering this data, and I'll be back in just a little bit. I've gone ahead and taken a number of more data points, finished off with this last one where there are 270 grams on there, and so we'll determine how much force that was that's being applied to the spring and that the spring is applying back. And when I measured that, that came out to 72.8 centimeters here. Of course, we need to subtract at 28.3 from that to end up with our actual how much the spring was stretched. So let me go get that data table ready. For reference, there's my raw data. I'm going to fill this out by determining what the force was for each values of this mass, and I'll do the subtraction to figure out how much the string actually stretched for each of those number of newtons of force being applied to the spring. Okay, so you see we've got the data all set up here. So the data table below summarizes the data that was obtained by measuring the length of the spring as different amounts of force were applied to the spring. Of course, that was by way of those masses being hung from the spring. Notice that it was actually the mass and the position that were the actual measurements made. The various weights that were added had known mass, and I actually measured the position of the bottom of the spring on the meter stick. The force was calculated as the force that was applied to the spring by the mass. Now I want to be precise here. Actually, let's take a look at what was going on. A force diagram of that mass, the hanging mass, looks like this. Notice there is the force of the spring, and if we make that complete, that would be the force of the spring on the mass by the spring pulling up, and down is the force of gravity. That would be the force of gravity on the mass by the earth. Newton's first law of motion, though it's an object at rest, staying at rest, so those two forces have to be balanced. Well, Newton's third law of motion tells us that if there's this force of the spring pulling up on that mass, well, then there must be that mass is pulling down on the spring. So we have a situation where there is a force being applied to the spring, and that causes the spring to come out to be stretched out to a certain value. So what we're going to be determining here is what is the actual relationship between that force and the amount that the spring stretches. Or another way to think about it too is if the spring is stretched a certain amount, how much force will it actually apply to an object? We will find that the amount of energy stored in the spring is related to that force that's applied, which therefore is also then related to the amount of stretch that there is in that spring. So just like we said before, the more a spring is stretched or compressed, although this particular spring couldn't be compressed, it could only be stretched, the amount that the spring is stretched is related to how much energy is stored in the spring. The more it is stretched, the more the energy that is stored in there. Also, the more a spring that can be compressed is compressed, the more the energy is that is stored in that spring. So if you'll notice that force value, those forces, because we know therefore that the weight of that mass is going to be equal to the force that's applied by the spring, and we know that the weight of that mass is just m times g, the mass times 9.8 newtons per kilogram. If we had a mass of 0.1 kilograms, multiply that by 9.8, and there's a force of 0.098 newtons. Similarly, if we have a mass of 0.1 kilograms, that's 100 grams, then multiply that by 9.8, and we have 0.98 as the number of newtons of force that is applied there. Notice how we actually got the value of stretch was we took the actual position that I measured of where the bottom of that spring was and subtracted that from that initial at rest position, and the difference between those two was the amount that the spring was actually stretched. So that force value and the stretch value are actually calculations that were made from the measurements. Well, your assignment then is going to be to graph the data to find the relationship between the stretch of the spring and the force that the string applies to the object. Now, notice that typically when we're going to graph experimental data, it's customary to graph the independent variable on the horizontal axis and the dependent variable on the vertical axis. Well, in this experiment, the independent variable was the mass of the hanging object, and then related to that, therefore, was the force that we calculated. That was the independent variable. The dependent variable was the position of the bottom of the spring, which we then calculated the stretch from, how much the change in position was, or the stretch of that spring. Therefore, the normal way that an experiment would be graphed, having the independent variable on the horizontal axis and the dependent variable on the vertical axis, would actually have force on the x-axis and stretch on the y-axis. However, and this is very important here, so I'm going to mark this with red right here. However, for this particular experiment, it's customary for physicists to graph the stretch of the spring on the horizontal axis and then the force that is applied by the spring on the vertical axis. You are going to make your graph in this customary way that physicists actually do it, rather than the more typical way that an experimental data is graphed. So you will graph, as it is written right here, the stretch of the spring on the horizontal axis and the force applied by the spring on the vertical axis. So after you graph this data, you're going to need to get a screenshot of that. So you should make sure that you have your graph scaled appropriately so that you can clearly see the line filling a large portion of the graphing area. I should not see it all squished up in one corner or one side of the graph. And you can let Desmos draw a straight line through your data so that you can see what the equation of the line, because you will find a line there. And just to remember that when you're going to get Desmos to give you that line, you can use that y1 tilde mx1 plus b to have Desmos do that for you. So when you've got that graph, you can insert a screen capture of that graph on the next page here, and you can see that there is space on the next page here. I've started your data table, so notice you start with a stretch of 0.008. That caused a force to be applied of 0.098 newtons when the spring was stretched to 0.026 meters, or 2.6 centimeters. Then the force was 0.196 newtons. You will want to fill in the rest of this data table from the table that's up on page 1. And then in this area here, you're going to actually put a screenshot of your Desmos graph in there. Then, of course, once you have the slope and the y-intercept of that line from that y1 tilde mx1 plus b, you will write in the slope and the y-intercept of that graph. And therefore, you know how to write this equation. The force, which is your y-axis, y equals mx plus b, y equals mx plus b, your vertical axis should be the force. So that's equal to the slope of the line times the stretch of that spring plus the y-intercept there. And then you'll want to read below for some of the key information, namely that slope is called the spring constant for a particular spring, And there are a couple of questions here that you want to think through physically. What do those values actually tell you? That slope, what does that actually tell you about that spring? And that y-intercept, you will find that it is not exactly zero. Why isn't it zero? Can you think of a reason why that might be? And finally, then down below, you'll want to take a look at that summary. And as you see down at the bottom, there are a couple of equations that you will find are going to be very important for us as we move forward with our quantitative look at energy, and in this particular case, elastic energy. Note in this case, we're not actually finding yet an equation for the elastic energy. We're just finding an equation for the amount of force that this spring applies based on how far the spring is actually stretched. We'll use this information to find out how much energy is stored in that spring. All right, you've got your assignment. Time to get to it.